Okay, so let's get started. Adam, is the recording on? Okay. All right, so we are going to get started. Let me start with some announcements. First is that this Friday, we are going to have a makeup class. Okay, same room, 2:30 to 3:45. Okay, so I will teach an extra class. There are two reasons for this. One is I have a lab out, as you know, and some of the material that we need to cover in that lab will be covered on Friday. And you know that Monday is a holiday, it's President's Day. So if you wait till next Wednesday, you will have the lab out for almost 10 days without having all the material. So I'm going to do that earlier. If you can, please come. Otherwise, as you know, it's recorded, it's live, so you can watch it on YouTube live or you can watch the recording. But I would appreciate if some of you come because there's good discussion that can happen while I teach that concept. Okay, so makeup class on Friday. Lab 1 is out. Lablet 1 is out. Okay, Lablet 0 is done. It's not graded, so you don't have to really worry if you didn't do it. But if you haven't, please do it anyway. Right? And if there are any other questions, we have daily office hours and there is Piazza. Okay, so I already announced all of them. Okay, so what we will, you have a question? Yes, the Friday class is same time as today on Friday, okay, in this room. Okay, all right. So we will continue from where we left off last time. We were talking about remote procedure calls. Okay, I explained what the concept is. I explained what the differences are from local procedure calls, and I was explaining that there is a marshalling and demarshalling of arguments, which has to take care of whether the machines have different architectural formats, big Indian, little Indian, whether they have different types of data formats for which you're going to use XDR, external data representation, where you convert all of your native data formats into XDR format, send it, and at the other end, you convert it back. This way, even if the sender and the receiver have different architectures, they can communicate without any problem. Okay. We do not allow passing pointers. Okay, there will be some material you see later where we can chase network pointers, but right now we assume that you cannot pass pointers in RPCs. Okay. And marshalling of arguments is called serialization in Java. We are going to talk about Java RMS today. Same concept, different term. Okay. They mean exactly the same thing. You have to deal with how parameters are passed back and forth. All right. The other thing I want to talk about before we move on to Java RMI is binding. Okay. So what does binding mean? Binding is basically the problem of how the client machine or the client application is going to find the server machine. Okay. Because as I said, you as the programmer are not going to provide lots of low-level networking details. You are programming using method call abstractions. Okay. The stubs have to take care of this, all of that for you. But how is the client to locate the server? Okay. So there's this notion of binding, which basically says that there is going to be some lookup service running somewhere in your network. Okay. So in RPC world, it's called the binder. In other programming languages, there's a different terminology that you use. But by and large, what you do is when the server starts up, it registers itself with that service, saying I am a machine and I'm an application rather running on such machine at this port number, and this is the service being provided. Okay. So then the client, when the first RPC call is made, okay, has to find where the server is running. So it's going to send a message to this lookup service, which we call the binder, okay, and say, is there a service running that provides this type of service, and which IP address is it, what port number is it, and so. Okay, so you essentially do a lookup, and then you figure out where the service is. If there is no server running, your RPC call will return an error saying the service is not running present. Okay? So that's a concept you have to keep in mind, because you will see that in RPC systems, the server has to register itself with some sort of service. Okay? The only way to get around that is that you have to hard code the credentials of the server in the client. You have to know that a priori, and then the code will only talk to the machine that is actually specified in the client. Okay? In this case, you don't have to do that. The client can run anywhere. You just need to figure out where it's running. Right? Okay. Few other things to keep in mind before we switch is what happens if there are various kinds of failures. Okay? You make a RPC request, but many things can go wrong. Okay? The client may not find the server. Okay? The server is not running. It's not registered with the binder. Okay? That's going to just give you an error. Okay? But what if the request message gets lost? Okay? You send a request, the RPC request never reaches the server. Okay? Now, if you're using TCP/IP and you use TCP as your transport protocol, this problem is going to be taken care of by TCP. It will figure out that the packet didn't reach and retransmit for you. You don't have to do anything at the application. Okay? But RPC systems don't assume that they will necessarily run on TCP. They could run on UDP. Okay? It's a different protocol. It does not do error handling. If packets get lost, you have to deal with it at an application level. Okay? So if you do this, then you have to introduce a timeout. If you haven't heard back from the server, you will retransmit. Now, this is an application resending the request, not TCP sending the packet. You are doing the same retransmission, but now at an application level. Okay. Now, what if the replies were lost? Okay, your message reached the server, RPC request. The server executed the RPC call, and it's a generated response, but that response message is lost. Okay. Again, if this is TCP, TCP handles it for you. You don't do anything. It will retransmit, and eventually a response will arrive. But if you're doing this at an application level, then the only thing you will see is that you sent a request, there's no reply. Okay? You are going to retransmit that request because you can't figure out whether the request message was lost or the reply message. You're just not hearing back from the server. Okay? So you will retransmit the request. Okay? The request is going to execute again at the server. Okay? Now, as you can imagine, this can cause problems if the server is making stateful operations. Okay? So if the request says, let's say you're sending a request to a bank server and say add $100 to this bank account. Okay? The RPC gets processed, a reply is generated but never reaches. Okay? The user is going to retransmit. And now if the application server, the server side of the application executes it again, you will see that now you have an error because you executed the same call twice. Okay? It's going to add another $100 to that one. So you don't want that to happen. Okay? So how do you prevent this from happening? You have to essentially ensure that all of your operations are idempotent. Okay? Idempotency is just a property that says no matter how many times you execute it, you're going to get the same behavior. Okay? So if you retransmit it and you execute it again, somehow you have to figure out that this message request was already received and executed. You do not re-execute that request, but you just send the reply back. Okay? That's how you are going to achieve idempotency in this system. So in some sense, the server will have to track all recently executed RPC requests and cache their replies. And if the same request comes back, and we'll assume that requests have numbers on them, right? So they have ID. So you know that request number 10 was already received previously. If you get the request 10 again, you will just look up this table and say it's already been executed. Here's the response that was generated previously. You just retransmit the response. You don't execute it again. Right? That's how you're going to achieve idempotency. Okay, there may be other ways, but this is one way. Okay? And there can be server failures as well, where the server itself fails to execute the request. So something goes wrong in the middle of execution, in which case you have to essentially re-execute. But then the question is, what guarantees are you going to provide to the end user? Okay, so what you want is what is called exactly once semantics, which says no matter how many times you retry, the server executes your call exactly once. Okay? That's hard to achieve. Okay, so you have other guarantees you can provide. No guarantee just says anything can happen. If you send it 5 times, it may execute 5 times. You have to deal with all the incorrect issues that will come out of that. Okay, at most one says, okay, when a call is made, it's going to be executed either 0 or 1 times. Okay, so at most once. Okay, at least one says you will have at least one execution. You might have more than one. Okay, and clearly, exactly one says if you send it once, it will execute exactly once. Okay, your question. Question is, who is going to make the system idempotent? Is that the question? Okay. So how does the system become idempotent? This is largely a server side issue. Right? If the server is receiving the same request multiple times, it should execute it once. Okay. So you have to deal with this at the server. The client doesn't know what's happened at the server because we just said the reply was lost. Client sent an RPC request, there's no response coming from the server. So all it can do is resend. And the server has to deal with this issue. Yes.
So basically, like you gave an example of payment. So every time I do a payment, there will be a new transaction item. So how will the server use that?
Okay. Question is, if you are making payments, every time you make a payment, it generates a new ID. Okay? So how does the server know whether it's been done again? So in this case, it's the application that's retrying the RPC call. The RPC call already has the ID, so it's going to just resend it. It's not that the user is doing. Okay, the application is retrying on your behalf, so the application will use the same RPC ID as before. It's called a transaction ID, but it's the same thing. Okay, all right. Okay, and then the server might fail, and then the client might fail. Client sent a request. Okay. Before the response comes back, the client has crashed. This can happen as well. Okay. What should the server do? Okay. So typically the server will send a reply and the reply will never reach the client, and that's the end of that. But there might be cases where the RPC call is a long running operation. Okay. You just sent an RPC to trigger a 1 hour long computation, okay, because there's nothing that says all calls are short. So if the execution is ongoing and the client has failed, what should the server do? Okay. So this says that the server can keep checking, is the client alive? Okay. The client is alive, it will continue execution. If not, it can terminate execution. So that is essentially what is the last of these properties, which gets expiration date. Every time you start executing an RPC, you have an expiration time. Okay. Let's say it's 1 minute. Okay. If the RPC is executing and that time threshold has passed, before you continue executing the rest of your RPC method, the server should check with the client saying, is it still up? If it has crashed and the RPC expires, then you just terminate it because there's no point continuing execution when there is no one to receive the reply. Okay? That's the expiration property. But there are many others. Okay, extermination essentially says that if the clients fail, you are going to keep track of this at the within the stubs and within the runtime systems, and you can essentially send a message to the server to kill what are called orphan RPCs. Okay? The client fails and the RPC call that the client initiated is still running is referred to as an orphan because there is no parent process that is there to receive the reply. So you essentially can track what orphan RPCs are present by just checking at the client side which processes are running and which are not, and then send messages to the server to kill orphans. Okay, that's called extermination. Okay. Reincarnations essentially says that you will essentially divide time into epochs. Okay, let's say 1 hour. Okay, every hour, at the end of every hour, you're going to figure out which calls are which RPC calls are still executing, which ones are failed. All the ones from the previous epoch are essentially terminated. Okay? So at noon, you reset everything that's still running is gone. You just start new. That's an example of reincarnation. Gentle reincarnation says that if maybe at the beginning of each of these epochs, you want to terminate old long-running RPCs, but before you do that, check if the client is still there and still wanting a reply. Okay, so delete only if there is no owner process there that's present to receive. Okay? All failure handling strategies. Okay? Any of them should work, but you need to decide when you implement an RPC system, which one is the one you are going to put in the RPC system so users can build their applications accordingly. Okay, any questions on this? Okay. So there are some quick implementation issues I want to talk about, but that's best done in the context of an actual case study, and which is Sun's RPC system. Okay. So this was the first RPC system that was designed maybe 40 years ago at this point. Okay. Late 70s, early 80s. Okay. It is still widely used. Okay. And this RPC system was originally designed for NFS or network file system. Okay, that's a client server file system widely used in Unix environments. We will look at it in detail when we get to the file systems part of the class. Okay, so the communication between a client machine, okay, and the server machine, as far as the file system was concerned, was designed using RPC. So file reads, file writes, file open, file close, all of the messages or all of the operations that the client was performing were sent as RPC requests to the server, and the file server at the server end would perform those operations and send back requests. Okay? That was the original reason they designed RPCs, okay? Or the NFS developers designed RPCs. And then they realized that this is not just a good way of designing a file system, it's a good way of writing any arbitrary application, because you can use the notion of RPCs to write other applications. So they took the RPC part from NFS and made a tool and released it as a standalone system, which could be used to write any arbitrary distributed app. Okay? And it's still used today. Okay? So original RPCs ran on top of UDP. They didn't have TCP, which meant that application programmers had to figure out if requests got lost, replies get lost, and deal with all of that. Okay? So it made the code more complex. So later systems switched to TCP as the default. You can still use UDP, but TCP is the default if you don't specify which protocol you want to use. In this case, a lot of the message losses are being dealt with by TCP as opposed to having to deal with it at the application. Okay. Now you can essentially see what they have done. So XDR representation came out of that RPC system. So that was the original definition of how you can make RPC system platform independent. It used at least one semantics, which basically meant that if your reply is not received, you are going to send the call again, okay, and then it will execute it again. Okay? There was basically no idempotency by default, because at least once means you can execute more than once. Okay? Then you got to deal with what happens if I execute that same call multiple times. Okay? So idempotency had to be dealt with at an application level. So all of these were features of this old RPC system that people still use. And your Lablet 1 actually has an optional part that gives you the code that I'll just talk about very briefly. Very simple RPC code that allows you to understand how an RPC system works. But this is the basic picture you want to keep in mind. There's a server machine at the top, the client machine at the bottom. Okay, when the server starts up, it registers with the port mapper. That's your lookup service or the binder. Okay? And Unix world is called a port mapper. Okay? And then when the client starts up and the first RPC call is made, it's going to contact the port mapper and say, where is this service running on this machine? What port? Okay? So then you get the port number. Then the stubs are going to essentially connect with the server, set up TCP connections, and all of those things that the stub has to do. Programmers don't do any of that. They just write the RPC methods and they invoke those RPC methods in the client. Okay, so you're still programming at that higher level of abstraction. Okay. Yes, there's a question. Okay, question is, when you register with the port mapper, what is the identifier of the server? So you have to give your server a name. Okay. So you can just say this is a hello world service. This is a print service. So you will essentially give a string that's a name that identifies it. You can give a version number as well. And then the port number is just the socket port where the server is listening for requests. Okay, and when the client is trying to locate the server, it has to use that name. It has to say, I need the hello world service, or I need the print service on this machine. Okay. The question, yes. Okay, question is, the port mapper allows you to identify the port. Does the client need to identify where the server is running? Okay, there are two answers to that. Okay, the simple answer is the many RPC system at least require you to figure out what machine the server is running, but not necessarily which port it is running. In this case, client can actually figure out by connecting to the port mapper on that machine and say where is the server. That's one. Okay. The second is there could be network-wide lookup services that actually tell you where the server is running, what machine, and the port mapper. In this case, there's one service running somewhere in the network. You contact the service and say, is there a service running with this name anywhere on my network? In that case, you will get the IP address as well. Okay? But the simple assumption is you need to know the machine name, not the IP address, at least the domain name, and then it will tell you what the port number is. The question is, there has to be a mapping of the host name. That is going to be done by the domain name service, or DNS. Okay, DNS is going to translate machine names to IP addresses. Okay, we don't need to worry about that. That's already a network service that's running. Okay, all you need to know is what the machine name is. Okay, IP address comes because of DNS, and then you have the port mapper. Okay, that those two pieces of information you need to know to connect. Any other questions here? Okay, so this is the process that you see or you have to use to generate an RPC client and an RPC server. Okay, on the left side, you have the client application. That's the one that's going to make RPC calls. Okay, at the top, there's a server application. That's the one that implements the RPC method. That's the function code that is in the server. And then you have something called a header or RPC specification file that basically lists all the RPC methods that the server exports, okay, and the names of the methods, the arguments, and so on. So think of it as an interface definition. The interface that the server is exporting is in this file in the middle. Okay? And then what you have is a special compiler in the RPC world. This is called RPC Gen. Okay? You just run the .x file through RPC Gen, and it generates a bunch of code for you. Okay? That is essentially all your stub code. Okay? And then what you are going to do is you are going to take your application, you are going to take the stub code, you have to compile it together, and you get a client bind. Okay? So that's the code the programmer writes. This is the code that's auto-generated. Okay? It's just C or C++ code if you're using a C or C++ language to do this. So you take that code and you compile it with the application, and you get your actual bind. And the same thing, there's a server stub. To take the server code and this auto-generated code and create a bind. And then you can just run the two, and it will do whatever we've been discussing. Okay, that's your workflow. Okay, so this is common in many scenarios where you essentially have a header file and there's some auto-generated stub code that is given to you. Okay. So you can take a look at this when you do that lablet. Okay. You will see that it actually generates, when you compile it, it will generate all these extra files for you that you can link to your application. Okay, so let me switch gears to RMI. So let's now talk about RPCs in an object-oriented way. Yes, you have a question? Yeah. Okay, question is the specification file going to reside on the client and the server? So what I showed you was the developer side of it, not the execution side of it. So somebody has to write the server code. Somebody has to write the client code. the specification file has to be common. Whoever is writing the server code has to write the specification saying this server has 4 RPCs. These are the names of the RPCs, methods. These are the arguments. Okay? So that has to be done. Now, the client code may be written by the same developer as the server, because you may be writing both the client and the server part. In which case, you'll take the specification and your client code and compile it, and the server as well. Okay? But even if the client is written by someone else, you have to at least provide the specification file for that client code to be compiled. Okay? Now, where you run it is orthogonal. This is just the development side, who's writing the code and how you are compiling it. Okay, so switching gears, we are going to talk now about RPCs in an object-oriented world, and they are called remote methods, because in Java you have classes, classes have methods. You are essentially invoking methods remotely. So it's called remote method invocation, or RMIs. Okay. So we'll first talk about few other RPC models you want to keep in mind. Okay. Before we get to RMIs, we'll talk about how RMIs are different from RPCs. There are some differences to keep in mind. Okay. And finally, we'll look at a bunch of these examples that you can then go and look at in your lablet as well. Okay. Same examples that are in your lablet are essentially covered here in brief. Okay, so let's talk first about RPC model. Okay. So we talked about a standard RPC application where there's a client, there's a server. Our implicit assumption so far was the client is running on some machine, and the server is running on some other machine, and they communicate over a network. Okay. Now there may be cases, special cases, where the client and the server are running on the same machine. Okay. There may be any number of reasons why you run a client on the same machine as the server. Okay. So a distributed application is just that you just happen to run on one machine. Okay. And the question is, in this special case, can we make the RPC runtime more efficient? Okay. Because if you remember, in normal RPC, when you make an RPC call, it's going to essentially make a message, is going to establish a TCP connection with the server, it's going to send that message, the message gets processed, and so on. Okay. So the client and the server are on the same machine. You don't need to set up a TCP connection to yourself. Okay. You can directly talk to the client and the server. Okay. So how do you make this more efficient? Okay. This model is called a lightweight RPC. Okay. It's a special case of the general RPC where client and servers run on the same machine. Okay. So what we are going to do is, rather than essentially use TCP/IP for the client and server to communicate, we are going to use shared memory. Okay. Rather than sending that RPC request over as a TCP message to the other end, why not just put that on a shared memory buffer and have the server just pick it up from there? Okay. It's going to do the same thing, but you don't have to deal with any protocol processing overhead or anything like that. Okay. So that's going to save you a lot more processing overhead that you incur in the general. Okay. That's the basic idea. In a lightweight RPC, you are going to use shared memory for the server and client to communicate back and forth rather than using network messages. Okay. So the way it's going to work is essentially your RPC execution, you are going to push your arguments onto the stack. Okay. You are going to then trap to the kernel. The kernel is going to look at that stack and somehow say, here is where the arguments reside. Let's make it accessible to the server side. And then the server side can then take that those arguments, execute it, and send it back. Okay. So in this case, the client stack, which is its memory page, has become available to the server. Okay. You can have another model where there is a special region of memory that dedicated as shared memory. Okay. So whenever the client makes a call, you can just copy your arguments into that memory, and the server can pick it up. Both of those would be fine. Okay. In this case, it's basically not using a special shared memory region. It's just taking the stack that the client has and just makes it available to the server. You just map that page into server address space, server gets hold of. Okay. And the responses come back the same way. Okay. There's a picture there, but it's not really showing you anything about stack. It's just showing you how you are registering yourself with the OS and so on. Okay. Now, most systems don't actually do lightweight RPCs. even if the client and the server run on the same machine, they are going to pay the full price of using network messages. The message basically goes to the OS and comes back up. It never goes on a network because the client and the server are on the same machine. Okay? So you just essentially use local host for communication. Okay? But you can do something like this to make that process more efficient. Okay? In an old OS which no longer exists called Solaris, it was a flavor of Unix. This concept was first introduced and it was called doors. Okay? A door just means it's a lightweight RPC. I don't know why they called it doors. Maybe they wanted to compete with Windows, but I don't quite know. All right. So which RPC to use? This you can be done using a runtime bit. Okay? So you could say that I write my code, okay? And if I have the bit set to true, it just runs like a regular RPC. If you set it the other way, that basically code uses a lightweight RPC. So you could use the same code to basically make use of essentially lightweight RPC and RPC. So you didn't even have to write that code twice. You just tell the runtime system, this is what you should use for the RPC. That was the flexibility that doors gave. Okay, yes, question. The question is, can you use simple IPC? You can use simple IPC on a machine, but shared memory was the preferred option. Yes, you can use other types of message passing. IPC just allows you to send messages back. Yes, yes, question.
Is this what happens after the lookup?
Okay, question is the first step in RPCs is a lookup where you try to locate the server. In lightweight RPCs, how do you figure out where the server? Okay, so there has to be, even in a lightweight RPC, some ability to first figure out is the server running. Okay, and you don't need to find the network port, but you need to at least find the process ID that you are communicating with, so you know where the server is. Okay, so there is some sort of a lookup process that's going to happen, but in the case of regular RPCs, that gives an IP address and a port. Here the IP address is known, it's the same machine. Port is irrelevant if you're not using TCP IP. So, but you need to know the endpoint, which is at least the process ID, minimally. Okay. Somebody had a question. Yes. Okay, so there are two questions. The first is where is the shared memory stored? Is there a capacity limit and so on? Okay, so there is most of the operating systems that you can you encounter actually have a concept called shared memory. Okay, so if you have used C or C++, you use malloc that allocates memory, or you use new that allocates memory and puts an object. That's just regular memory. But you can make a special call saying make a shared memory segment. So then you get a special type of memory called shared memory, which you can explicitly share with other processes. Okay? Shared memory segments are specifically designed to be shared across multiple processes. Because by default, you cannot allow some other process to access your memory. That just doesn't happen because the OS prevents that from happening. Okay? So you can use OS mechanisms to allocate and deallocate shared memory, just as you use regular memory allocation mechanism. Okay, that's the first question. The second question was, how is the runtime bit determined? I said you don't have to worry about it. What I was trying to say is the programmer does not have to worry about writing two versions of their code, one for the special case where it's a lightweight RPC and one that's regular. You just write the same code, but when you compile it and when you run it, you can say run this using the lightweight RPC libraries or run this using the regular. Then it can make that choice. Okay. Any other questions? Okay. So very quickly, there are a few other RPC models to keep in mind. We won't go into them in too much detail now, but we will come back to them later on. Okay, the three are asynchronous, deferred synchronous, and one way. Okay, I'm going to show you some pictures. That makes it clear rather than explaining that slide. So this is our standard RPC timeline. These are blocking RPCs, also called synchronous RPCs. Okay? Client, so x-axis is time, top is client, bottom is server. Client executes, makes an RPC request, and is going to block for the reply. Okay? Just as a regular function call, the caller waits, or the callee waits for the called function, right? So that's the same thing. So you are essentially going to wait and then execute once the reply comes back. That's synchronous. Okay? Asynchronous RPC essentially is non-blocking RPC. Okay? You make a request, which is an RPC request. Okay? You send that message, okay? And then you're essentially going to just get an acknowledgement that the server received your request, not yet executed. You don't have a reply. Just have an ACK saying the request was received at the server, okay? And then the client continues execution. Okay? The server is asynchronously going to execute that call and then send a reply back at a later time. Okay? So the client is not blocking for the server to produce a reply. It's only waiting to make sure your call was received at the server. Okay? That is asynchronous RPC. Okay? Deferred synchronous RPCs are two asynchronous RPCs, one in the forward direction, the other in the reverse direction. So you make a call, okay, and then you get an acknowledgement saying the RPC request was received. Client continues execution. Okay. The server is then going to process that call. So it's going to execute that RPC call and at some later point generate a reply. Okay. And then a reply has to be now communicated with the client. Okay. This is done using a reverse asynchronous RPC where you basically send a reply, okay, and then you wait for an acknowledgement and you continue. And the client will just receive that reply and then process it. Okay. So deferred synchronous are just two asynchronous RPCs, in one in the forward direction, one in the back direction. Okay. And then there is one more that I don't have a picture for, which is called one-way RPC. In one-way RPC, the client makes a request, but it doesn't even wait for an acknowledgement for the server. So it's truly asynchronous. You make the request and you proceed. You continue execution. Okay. So whether the call was received or not, you don't really wait. Okay. That is essentially called one-way RPC. Okay. Other methods for thinking about how to implement RPC system. By default, the most common approach is the synchronous approach because that's what is easiest to understand. You make a request, wait for a reply. And so that's an easy method. But there are these other things as well that you can use. Okay. So with that background, let me switch to Java and Java RMI. Okay. So as I said, RMI stands for Remote Method Invocation. Okay. This is essentially RPCs in an object-oriented world. Okay. So how is that going to work? So when you write a class, okay, and then you instantiate the class as an object, the object has some methods in it. It might also have some data encapsulated in it. Okay. Other objects can call your methods. Okay. And by default, you assume that all of the objects reside in one process, so they can call one another or call one another's methods. Okay. In RMIs, we assume that these objects are not going to be in one machine or one process. They can reside in different processes and possibly on different machines. So now one object, okay, can invoke a method belonging to another object that resides on some other machine. Okay. Very similar to RPC. So you just say object.foo, okay, and that foo is the method. It's just that object and foo are both on some other machine. Okay. So you have to do equivalent of what you will do in an RPC. To execute this method, you have to send a message to the process that's on the other end, and then that has to execute that method and send back a reply. Okay. That part is the same. Okay. But doing this remotely is basically where we have to think about how Java might be different from RPCs. Okay. Now, one thing that Java supports, which we can take advantage of, is what we call system-wide object references, which means that you can refer to objects that reside on other machines and other processes, and somehow we'll be able to track it down. Okay. And we'll use that to our advantage, and you'll understand what I mean. Okay. So the main difference because of this is you will be able to pass objects by references, okay, in parameter passing, and we'll get to that. But let's look at a picture first. Okay? This picture should look very much like an RPC picture, right? Except that this is now all object oriented. This is the client machine on the left. There's a server machine on the right. Okay? Both of these client and the server machines are essentially going to use RMIs. Okay? We still have the concept of a stub. In the Java world, just the terminology is different. The client-side stub is called a proxy. Server-side stub is just called a skeleton. Okay? It's the same thing, but that's the part that you don't write it, generate it for you. Okay? So the client is going to invoke a method. Okay? That method is essentially going to go to this proxy object, is going to invoke a method on the proxy object. You know that that's a remote method. So you're going to send that request over a network. It arrives at the server. The server is where the actual object resides, as shown in that gray box. You're going to invoke the requested method on the server, execute it, reply is going to go back the other. Okay? So it's very similar concept to RPCs. Okay? But now you can write Java code where you will have to essentially write two Java programs, one that's the client, one that's the server. The client can call methods of objects that reside on the server. Okay? That's basically what you will be able to do. And it's very straightforward once you understand how to write it. It just looks like you're calling any method on a Java object. Just so happens that this is a remote object. Okay. All right. So I think I mentioned all of this. The proxies, the client stub, the server stub is called the skeleton, and marshalling and demarshalling of arguments is called serialization and deserialization. Okay. That's a broader concept because Java can serialize object. Even if you want to store an object on disk, not necessarily use RMIs, you can just essentially take the object and you just construct a byte stream out of it, and you can store it on disk. Okay, that's what serialize does. Deserialize will reconstruct. You can use that same concept to send parameters on RMI calls. Okay? You can take any set of arguments, whether they are simple integers or other data structure or entire objects. You're going to essentially marshal them using serialization and demarshal them at the other end. Okay? This is also going to give us platform independence. Same thing we had in RPCs. Okay? Your Java code can run on arbitrary platforms. Right? So long as you have a JVM, you can run it on Windows, you can run it on Linux, Mac, any number of platforms. Okay? But all of those architectural differences still exist. Okay? It could be a 62-bit machine, 32-bit machine, and all of that. Now, Java does provide us abstraction that hides lots of this for us. But as far as RPCs are concerned, you want to make sure you are when you send something from the client to the server, if it was little Indian versus big Indian, you can deal with those differences. Okay? Which is why you have to essentially do all of this extra work. Okay? Very same concepts as RPCs. Okay? Now, here is essentially two ways to bind a client to an object. Okay? This is more abstract. This is not specific to Java. Okay? One is called implicit binding. The other is called explicit binding. Okay? In implicit binding, you essentially have an object. Okay? That's a remote object, and you call a method on that object. That's an RMI call. Okay? So the first time you make an RMI request, okay, your stub code is going to go and figure out where the server is and bind to it. Okay? That's called implicit binding because the user, not the user, the programmer hasn't essentially written any code to bind. Okay? The other approach is explicit binding, where you have to first bind to that object before you can call methods on that object. This is going to essentially go to a port mapper like services called RMI registry, okay, in Java world. Okay? And it's going to figure out where is that object, okay, how do I connect to it, all of that, and then you can call methods on that object. Okay? So it's either implicit or explicit. Many programming languages just require explicit binding. So you have to have a bind call somewhere in there. And I'll show you examples. Is this clear? Okay. All right. So let's talk about parameter passing. Then I'm going to show some sample code. Okay. Now, parameter passing in RPCs was pass by value only. Okay. You cannot pass pointers. You could not point pass references. Okay, that's slightly different in this case. There's a question. Yes.
The previous slide, okay, RPC,
Yes.
okay.
Yeah. The question is, which is actually in this slide. What is the difference between RPCs and RMIs? That's what I'm trying to explain. In RPCs, you can only pass parameters by value. Okay? There is no passing by reference. You cannot pass pointers because pointer is a memory address on that machine. If you pass a pointer and you dereference it on another machine, it's going to point to that memory address on that machine, which is meaningless because you have intended some other address. Okay? So no passing pointers. Okay? In the Java world, you pass all arguments by value, okay, except one exception, which is there are some objects that can be passed by reference. Okay? So if you declare an object to be a remote object, okay, which means that this object exports methods that can be invoked by other objects, that object, if you pass to a method, it will be passed as a reference. Okay? Because you can't pass it by value. It has to by definition reside on the server. Okay? Anything else that you pass to an RMI call will always be passed by value. Whether it's an integer, whether it's an entire local object, they'll all be passed by value. Okay? So the default is still passed by value, except if it's a remote object. A remote object is a special class that you've written that accepts RMI calls. Those objects are the only things that you can pass by reference. Okay? That's the difference between the two. Okay? And this is a complicated picture, but all it is showing is there are three machines. Okay? There's machine A, there's local object O1, there's machine B, there's a remote object. Okay? Now, if this machine calls yet another object that resides on the third machine, and it wants to pass a reference to O2, that will get passed as a by reference. But if it passes O1 as an argument, that's going to an entire copy of O1 is going to go over the link. Okay? Because the entire objects are local objects are going to pass by value. So the code and the data for that object will go by value. Okay? That's the difference between the two. Yes, question. Okay, question is, can you ask C to have a reference to O1? You will see that because you passed O1, it was passed by value and as a copy of O1 here. The only way you prevent that from happening is you have to make O1 a remote unicast object, okay, or unicast remote object, which means it will be a remote object. That's the only way Java will pass it by reference. Otherwise, it will pass it by value. Yes, question. How is the memory allocation for a remote object work on a local machine? So remote objects are passed by reference, right? So you just have a reference to the object. You don't have the actual object itself, right? So then when you try to call a method on that object, it is essentially going to go as a message to that actual object. So you don't have to have a lot of memory because you're just storing a reference. It's like storing a pointer. Okay? Yes, a reference is a memory it's IP address and a memory location of that object, not the object itself. The object itself may be large, but you don't store it, you just store a reference to it. Okay, anything else? Okay, so now let's look at some code. So this is going to become a little more real in some sense. And this is all the stuff you are going to also look at in Lablet 1. There are several examples of RPCs and RMIs and whatnot, which is background you need to have to do the lab. Okay, because the lab is actually asking you to make RPC client server applications or RMI, depending on whatever language you choose, okay, whether it's Python or Java or C++. Okay. So let's talk about Java RMI. Okay, I already explained that a Java RMI application will at least have one server, can have more than one, and a client. Okay. The server is going to define your interface. That's the set of methods it is exposing, and then it's going to implement each of those methods. So each of the interface method has to have an implementation. Okay. To define the interface, you then implement code for all the methods. Okay. And then the server program is going to create the server object, and it has to register it with the binder, which we will call the remote object registry. It's called RMI registry. Okay. The client has to look up the server in the remote object registry, and then it is going to use normal call syntax, okay, to make remote object. And as I said, RMI registry is the server side name server. Okay. Here is some code. I don't know if you can see that in the back, but so the code has multiple parts. Okay, this is the interface. Okay, so you will say essentially that you are going to define a remote object. Okay, so you essentially say extends remote and say it has one function. Okay, the function is called say hello. That's the method that you can invoke remotely. So there's a hello object, and it has one method that has been exposed to other clients. Okay, and that's the only thing you can call. Even if the object has other methods, those would become local to that object. Only the ones that are exposed through this interface are the ones that you can actually call remotely. Okay, that's your interface, okay, definition. Okay, this is the server. Okay, there are 2 or 3 things you have to see. First is you declare a unicast remote object and say this is a remote object that I'm going to invoke. Okay, you are going to then bind the object. So there's a registry.bind which says I am the hello service. Okay, so you bind yourself to the remote object registry saying I'm a server, my name is hello, that's a service X. Okay, and then you have to actually, there's extra code here not shown, you have to wait for essentially that method to be called. Okay, the method itself, say hello method, is not shown here, but you have to have the implementation. Okay. On the client side, you have to first do a lookup. Okay, so there's a registry.lookup call that's saying where is the hello server running. Okay, and that's all. You don't need to then worry about IP address or anything like that. The stub code is going to do that for you. Okay, and then you will see that there is stub.sayHello. That's your RMI call. Okay, just looks like an object.method syntax. Okay, there is no indication that that's a remote method or anything like that, just normal call syntax. Okay, there's some exception handling there you can ignore. Okay, that's a typical prototype skeleton of a Java RMI program. Any questions on this? Okay, so let me talk a little bit about synchronization, and then we'll look at other code snippets. So first thing is, when you write a client server application, you will have to use synchronization in many cases. Okay? The reason is your server is often going to be concurrent. It will use threading because multiple clients can connect to it and make concurrent requests. If you start processing requests sequentially, okay, requests are going to have to wait for a long period of time. So typically servers will have threading where each thread can then process a request concurrently when other threads are serving other requests. Okay? If you have threads, it should be clear that you have to have synchronization. You have to ensure that any shared data structures have locks and whatnot. Okay? Now, Java has built-in support for synchronization. You can use locks, but Java has this concept of monitors that allow you to have automatic synchronization on objects. You can make any class into a monitor class, and a lock is automatically provided for you by Java. Okay? In that case, only one method of that object can be called at any time because that object, that thread that's executing will hold the lock. If some other thread tries to call another method of that object, it will block, okay? Which is what locks allow you to do. Okay? So by default, you can just use monitors to do synchronization, or you can use explicit locks, okay, which is also supported. Okay? Now, suppose that you use monitors in Java, but this is a distributed application. The question is, if the lock is in use and another call comes for that object, that call has to block. Okay, because the lock is in use, you have to wait for the lock to be released. Okay? And then as an implementation design question, the question is, where are you going to block? Are you going to block at the client side? You don't actually send the request to the server until the lock is available, or you send the request, but it's now blocked on the server side, waiting for the current thread to finish. Okay? And depending on which of these two you pick, there can be implications on when failures can occur. Okay? If you block at the server and the client crashes, then you will have issues to deal with, saying what do you do if the client is already holding the lock? Okay? Now, if you block at the proxy, okay, then multiple clients will have to coordinate a lock. You will need a distributed lock, okay? Because all these clients have to figure out when they can grab the lock. They haven't even sent the request to the server. If you sent the request to the server and you just implemented a simple lock, that's not a problem. But if you block at the client side, then your lock has to itself be a distributed lock. And we'll see how to implement distribute locks later on in this class. Okay, we are not going to do that now, but these are things you have to keep in mind when you implement synchronization for distributed applications. Okay? You have to have locking. How is the lock implemented? Is it centralized at the server? Is it distributed at the client? These are all things to keep in mind. Okay? Now, Java does use proxies for blocking, but it does not actually implement locking by itself. It leaves that to the designer. Okay, so you will block at the proxy, but if you have synchronization requirement, you have to implement your own lock. Okay, it's not going to give you a built-in lock. Okay, this is something to keep in mind. Okay, so I already showed this picture. I'm not going to go through this again. If you do whatever I showed you previously in C or C++, you essentially have to write that interface that I showed you in the Java thing. That's going to go into this .x file. The client code goes in the client side, server code goes there. This is how you compile it off. Okay? You are going to use a tool called RPC Gen to compile the header file, okay, or .x file. It's an interface definition file, not a header file. And it is going to generate all of this extra code for it. You'll see that one of that is an XDR file. Okay, that because all of your communication has to use XDR, so that's going to do that part for you. Okay, that's the server stub, that's the client stub. Then you take all of this and you compile the application. Okay, I don't have snippet of a code, but it is there in the lablet if you want to take a look at this code and compile it. Okay, let me show you. I did this already, so I'll skip this. Let me now explain how you do this in Python. Okay, if you're going to write your lab in Python, and you want to use RPCs or RMIs, you have to use something called Python remote objects or Pyro. Okay? So right now we are at Pyro 5 or version 5 of Pyro. So here is some snippet code that shows you similar concept. Okay? So you will see at the top is your server code, okay? The top box. Okay? You will see that there is that's a greeting Apple server. So you will see that it's registering itself. Okay? Just as in the Java code, you registered the server with RMI registry. Pyro also has to register itself saying this is a remote object that can be called. And then you're just going to sit in a loop waiting for request to be received. Okay? Now, and then you can actually start executing that server. Okay, that gives you a URL that you have to use at the client. So here is the client code. Okay? So first, you're going to look up, okay, get a proxy to look up the server. But then this is the actual RPC call. You'll see that it says greeting maker.getFortune, okay, which is just object.method. Okay, same concept. Okay, all of this are going to look exactly the same. You are not dealing with networking concept. You just declare an object on the server. You just call the object on the client. Okay, you just have to do the binding part to make sure the client knows where to find the server. Okay, and here you will see that there are ways to actually look up the server, where you look up the server is registered with a proxy. That's the name server. You basically give the name of the server. Like where is example.greeting server running? Okay, that's the name that the server has picked in this case. So you look it up and then you can make a call. Okay, is this clear? The same kind of concept, but now you are in the world of Python. Yes, question. Yes, Pyro. The question is Pyro wrapping RPCs. Pyro is essentially, think of it as the RPC runtime in Python. Okay, it's going to do all the extra work for you. You're just going to declare your server, you register it, and write your methods. And at the client side, you bind, not bind, but look up, and then you call the methods. And Pyro will do all the heavy lifting for you. Okay. Yes. Question. Question is this compatible with Python 3? This is all Python 3. Okay, your lablet has the same kind of Python example. Okay, so go and if you want to try to write your code in Python, you will see how that works. Okay, so we have in the lablet a Java RMI, a Python There's gRPC that I'm going to talk about, and CRPC. There are 4 parts in the lablet, 4 ways to do RPCs and RMIs. It's good to see the sample code. You don't have to actually do much because you just have to run the code, look at it, and see how it works. Okay. Any questions on this? Okay, so that's Python. The last system we are going to look at is gRPC. There's Google's RPC platform. Okay, so Google went and built an RPC platform which was designed for high performance applications, and then they released it. So now you can just get it as open source and you can run it. And in fact, your lab 1, actually part 2 of lab 1 requires you to write your code using gRPC. Okay, it's a modern version of what I showed you. RPCs are old, Sun RPC. This is the modern way people write distributed applications. Okay, so what is gRPC? First of all, it is a platform independent RPC system. It works across, like any other RPC system, works across OS and hardware. But importantly, in this case, it's also language independent. Okay? You can write the server in gRPC in one language, and you can write the client in a different language, and they'll still communicate with one. Okay? In all previous systems, the client and the server had to be written in one language. The platform could be different. Your OS could be different. In this case, even the language can be different. Okay? So languages that are supported are Python, Java, C++, C#, Go. I think there's Rust, Swift, Node.js. There's a whole variety of languages and systems supported for gRPC. Okay? Now, the interesting thing in gRPC is it does not run over TCP, which is what RMI and RPC systems and even Pyro are going to do. They actually run on top of TCP. Okay? gRPC runs on top of HTTP. Okay? Your RPC calls from the client to the server actually go as RPC HTTP requests. Okay? RPC replies come as HTTP responses. Okay? So they have layered RPC on top of HTTP. So HTTP is the transfer. HTTP itself runs on top of TCP. Okay? But your client request is essentially going to be become an HTTP URL and go off to the server, and the server will process. Okay? So it is layered on HTTP. That's an important difference from the previous systems. Okay? And that's one. The second thing is there is something called protobufs, which I'll talk about. So that's essentially the method by which you are going to send arguments, so get back responses, and so on. So protobufs are going to essentially do the serialization and deserialization for that is the XDR format in gRPC world. That's how you are going to make sure that whether you are running on Windows or Linux, or you're sending this from Java to Python, it will all work. Okay? Because that is the standard that we are going to use for message passing. So the client and the server understand structure of messages because they're protobuf messages, a special type of message. Okay? No question, yes.
There is an extra layer.
Yeah. Question is gRPC faster than RPC? Hard to say. You can do measurement and figure out. Okay, because there is an HTTP overhead, but there are other things I'll talk about that are not there in RPC systems, which will make it more efficient. Okay. Standard request response, perhaps not, because you are sending HTTP messages. TCP will be faster. Okay. But there are other things we'll talk about in just a second. Okay. So let's talk first about protobufs, because first concept you need to know to write your RPC application is you have to first define your message structure. Whatever message the client and the server are going to exchange, which would be arguments and replies to arguments. So what arguments you pass to a method in RPC, gRPC method, and what replies you have to declare as protobufs. Okay? So here is essentially a protobuf example where you are going to make a search request. That's a message. Message says this is a search request. So it has a required argument called a query string. Okay? And then it has optionally a page number and a result per page. Those are optional messages. Okay? So you can say, here is what the client is going to send. It's going to send a string. It's a query. Okay? And so essentially you say it's a string and a query, and the other arguments are 32-bit integers and so on. Okay? So once you declare this protobuf, you are going to use a special protocol compiler. Okay? The protocol compiler is going to generate some stub code for you, similar to an RPC system. Okay? So that's essentially going to let you send these protobufs across systems and whatnot. Okay? Now, the thing you want to keep in mind is if you have done any HTTP programming or know any HTTP, when you send HTTP messages and many times the response come back as JSON objects. Okay? JSON objects are essentially ASCII. Okay? You should think of protobufs as a binary version of that because it's more compact. Rather than sending ASCII strings, you essentially send back replies as binary messages in HTTP responses. So instead of getting a JSON response back, you're going to get a binary response that corresponds to a protobuf you're declared. So it has a structure. The structure is just binary. It's not ASCII as you might have in a JSON objects. Okay, and this is done for efficiency reason because the replies are going to be shorter than sending ASCII messages, and the requests are going to be shorter in size. Okay, so first concept is before you write your RPC request, you have to first think about what messages are going to be sent, what replies are going to be coming back, and you declare the structure. Okay? If you have 3 arguments in a method call, you make a protobuf with those 3 arguments. Okay? Because that's what is going to go. Okay? Once you do this, then you start actually declaring the RPC methods themselves. Okay? With the previous one just said that's a buffer, that's not a request or a reply. So now you have to declare what are the methods and what are they going to return. Okay? So you do this by declaring your gRPCs in the proto file itself. So here now you will see that you said there is a service called greeter. It's a hello world service. Okay? It has one RPC method, it's saying say hello, and it takes one argument which is a hello request. Okay? And it sends back one response which is called a hello reply. Okay? The hello request and the hello reply are protobufs. You have to declare their structure. This doesn't tell you what is in them. It just says there are 2 buffers. The input buffer is called a hello request buffer. The reply buffer is called a hello reply buffer. Okay? Here is where you are now declared what the input is going to look like. So you say hello message, hello request is a message that is a string. Okay? That's your protobuf definition for the input. Okay? If there are 7 arguments, you would declare all of them in that protobuf, one at a time. Okay? In this case, there's only one argument, is a string. And you say the reply is also a string. I'm going to send a string and it's going to send back a reply. Okay? That's your protobuf definition. Okay? So you essentially said, here is a service. Okay? That's my server. It has one RPC that it has exposed. Okay? That's a gRPC. That's the name. Okay? And this takes this argument. That's a protobuf. That's a reply. That's a protobuf. Then you use your protocol compiler to compile. You get the client stub code. Okay? And then you will essentially also have a gRPC server on the other side. Okay? We haven't yet written this service. Okay? That's something you have to write. This is just the declaration of the service. Okay? So you will declare it this way, and then you have to write it in whatever language you want. Is this clear? Yes, question. Okay. Question is, why does Pyro not need a protobuf-like system? Okay. In Pyro, both the client and the server are Python programs. Okay. So the Pyro has internally declared how messages are going to be passed, how arguments are going to pass. So it has its own external data format. Okay. So you don't need to declare it. You have to do all of this simply because you want language independence. You are going to send your request from a Python program, and it is going to be received by a Java program. Okay? That typically requires you to have more understanding of what you're sending. A Python argument may be something that a Java program doesn't understand. So you have to do extra work to say this is what it's going to look like. So when a Python request comes, you can interpret it. Okay? So when you have language independence, you have to do this extra work. In Python, you don't assume language independence. Everything is in Python. And same in Java and C. Okay. Question is, since Python is interpreted, do you not need to know the method definitions ahead of time, or do you? you still need to declare all your methods item. Just because it's interpreted doesn't mean you can bind at runtime. There are systems that can start running without even knowing what the RPC method name is. But I don't think any of the systems we talked about do any of that. You have to declare all of them ahead of time. The client needs to know what the server methods are and call them and what. Okay. Any questions here? Okay. So let me now explain. There was a question about, is gRPC actually more efficient than RPC because it's using HTTP, it doesn't use TCP. And I said it depends. Okay. Why does it depend? Because gRPC actually supports 4 types of RPC calls. Okay. There's something called unary RPC, which is our standard RPC. You make one request, you get one reply. Okay. That is what we are going to call unary RPC. That's the default case. Okay. But there are 3 other types which support what are called streaming RPCs. Okay. Streaming RPC says that you can receive for one request more than one reply. Okay. You send a request, you may get a number of replies. So you don't stop after the first response is received. Okay. You can wait, another response might be received. So it's a stream of replies that are coming back. Okay. That's called server streaming. You send a request and the server is streaming a set of replies to you. Okay. In a normal RPC world, you would have to make n calls to get n responses. In gRPC world, you can make one call and get n responses so long as they are related to one another. Okay. You can use streaming RPC to do that. Okay. You can also do client-side streaming, where the client is streaming a set of messages to the server receives all of them, it processes them, and then sends back one reply. Okay. Think of a sensor. Okay. A sensor, maybe a temperature sensor. It provides a sequence of readings. Okay. You might say, I'm going to send 10 readings and then have the server process them as a batch. Okay. So you can send them as a client stream RPC, saying here's a stream of data, and you just send them. And then once they're all received, you can get a reply. Okay. You can do these kinds of things which you couldn't do. Because in a unary RPC, every data is sent as a single request, you get back one reply. So you are now amortizing the request calls across multiple data items by sending them as a stream. Okay. And you have bidirectional, which says the server can send a stream, the client can send a stream. Okay. You can send a stream of requests as arguments, you can get a stream of reply from the server. Okay. So these are these are 3 RPC features you have not seen in Pyro or in RMI, Java RMI, or in C, C++ RPC, which gRPC will support. Okay. Advanced things which we will not really look at in this class, okay, but you should know that they exist. And when you use them, then you can think that the system will actually be more efficient because it is reducing the number of requests you make. Okay. Any questions? Yes.
This allows
Okay, question is the HT reason we use HTTP is because we are streaming? I think that is not really the reason they're using HTTP. HTTP has just become a very common way by which services communicate. So they just chose that as a way to implement this. But I did mention, I should have mentioned this, that there is a specific version of HTTP that it uses, which is called HTTP2. Okay? HTTP2 actually has some optimizations that make this type of interactions much more efficient. Okay? And when we talk about web, I think in many classes from now, we will talk about HTTP2 and understand what it does and how it works and so on. Okay? But that's by and large the reason. Yes, this question.
ARPC uses that server, and is this another version of this?
Okay. Question is, does gRPC need a web server because it's HTTP, and is it another version of a REST protocol? The first thing is a gRPC server. When you compile it, you don't actually run a separate web server. The gRPC server itself will have the capability to receive HTTP requests. Okay? So there will be a library that's built into your server that can process requests, RPC requests that come in as HTTP requests. So you're not sending this to a separate web server. Okay? That's the first thing. The second thing is just saying, is this a REST API? So you should understand that REST API requires you to have URLs you define as resources. Okay? Here, you are just defining methods. You are not defining HTTP URLs as resources. You are just defining methods and responses. It just so happens that they are getting layered underneath over HTTP. You don't get to decide what that HTTP format looks like. So in that sense, it's not RESTful, because in RESTful API, you are going to define your method name as an HTTP request. So you will say foo.say hello. That's your HTTP request. That's not what you do. You're just writing regular methods. Okay, so it's different. Okay? So two more things very quickly. gRPC supports both synchronous and asynchronous. Remember at the beginning of the class, I explained what synchronous and asynchronous is. You can say the same request has to go asynchronous. It will do that. By default, it will use synchronous. You can specify deadlines and timeouts. You can say, here's a timeout. The server hasn't responded by this time, return. So you don't have to block forever. Okay? So it will allow you to do that. You can also cancel the RPC. After you send it, you can say cancel it, and then the server and client will terminate that RPC call in midstream. So all extra functionality that has been provided in this RPC system. Okay, so we'll stop here today. And I want, for those of you who came late, I just announced at the beginning of the class that on Friday we'll have a makeup class. Okay, in this room, same time, 2:30. Okay, and we'll talk about concurrency models.